Hi, my name is Ben Berg, and today I'm going to talk about the case for PhaseAware scheduling of parallelizable jobs. This is joint work with Justin Whitehouse, Ben Moseley, Weina Wang, and more Harchol-Balter, and we're in the computer science department at Carnegie Mellon University. So the reason I'm talking about parallelizable jobs today is that the world is increasingly parallel. And this really starts with a trend in system design. So if we think about what system designers are doing to increase performance today, they're doing things like packing more cores into a single multi-core server, wiring many servers together via fast networks to create rack-scale computers, and co-locating many racks of servers to form large-scale data centers. And as a result, if we look at many applications like databases or machine learning applications or scientific computing applications, all of these use cases are being designed to try and fully exploit this underlying hardware in parallel. So this in turn poses a whole host of interesting theoretical and systems questions about how we should be trying to run these workloads on these underlying systems. And I'm going to consider a particular example here in today's talk. I'm going to think about trying to run an in-memory database on a single multi-core server. So to begin to consider this question, we'll construct a basic model of a database. So here's our database running on k equals 16 cores. And this database is going to be tasked with processing some queries. And we'll assume that queries arrive to the system over time with some average arrival rate like lambda queries per second. And when queries arrive to the database, they can be parallelized across many cores. So here I've drawn query 1, this blue query, being parallelized across all 16 cores. Now for each query, we'll measure what I'll call the query's response time, which we'll define to be the time between when a query arrives to the system and when it's complete. And in general, in today's talk, our goal will be to minimize the mean response time across all of these queries arriving to the system. So this really raises two central questions that I want to talk about today. The first is sort of a modeling question, which is how do we model the benefit that a query receives from being parallelized across additional cores? And the second question is, in light of this first question, how should we choose to split the cores between the various queries in the system? So for example, I could have chosen a different allocation here. I could have allocated, 4 cores to each of these queries. How should I choose to allocate cores in order to minimize the mean response time across queries? But let's start with this first question of how to model the benefit of running on additional cores. So to tackle this question, I'll start by introducing the notion of job size. And here we'll define job size to be the running time of a job on a single core. So you can think of job size as reflecting sort of the amount of inherent work associated with a job. And in the case of running queries in a database, you can think of the query size as being related to like the number of tuples that have to be processed in order to complete the query. And once we understand a job's running time on a single core, we can then think about how the job's running time changes on k cores. And this is often described via a speedup function, s of k, which tells us how many times faster a job runs on k cores than on a single core. So for example, I could put cores on the x-axis here and the speedup function s of k on the y-axis, and we might hope that a job receives a speedup function like this green line. Now this would be an ideal speedup function because it would tell us that the job runs 4 times faster on 4 cores and 6 times faster on 6 cores. But what we see in practice is that a more realistic speedup function is this purple line, and that in practice jobs receive some sublinear concave speedup from additional cores. Finally, we can combine the notion of job size and speedup function to calculate a query's running time on k cores in our simple model of a database. We take the query's size, its running time on a single core, and divide it by its speedup, s of k, to get the query's running time on k cores. I'll refer to this as the speedup function model. The speedup function model has been used widely in both the systems and theory literature, including some of my own work. The speedup function model is useful for modeling a job's running time in many systems, but it does have one key problem, which is that it assumes a job's behavior is constant over time. For many applications, however, jobs change over time, meaning that a single job will consist of multiple distinct phases, each with their own scaling characteristics. This is definitely true in databases, but it also applies to the other applications we saw earlier, such as machine learning and scientific computing applications. So to see what I'm getting at here, let's consider the example of this concave purple speedup function. Where does the shape of this speedup function really come from? Well, for most jobs, this has something to do with Amdahls Law. Amdahls Law observes that if only a p fraction of a given job is parallelizable, then even if I run that job with a high degree of parallelism, the sequential portion of the job will eventually become the bottleneck and result in a concave sublinear speedup function. Note that encoded in Amdahls Law is an assumption that a speedup function is only measuring a job's average speedup over time. However, it's possible that that p fraction of the job, which is perfectly parallelizable, all happens at the beginning of the job during some elastic phase, perhaps while the job performs some big parallel computation. This could then be followed by some inelastic phase where the job is completely sequential, perhaps while we coalesce the results of that parallel computation. Note that a job consisting of these phases could still exhibit an average speedup function that's consistent with the speedup function model, despite the fact that the job never really followed this purple speedup function at any one moment in time. If we return to our example of queries running in an in-memory database, we can see that this is exactly what's happening in this case. I went and measured the speedup function for a query from the star schema benchmark running in the open source noise page database. It exhibits a speedup function that's concave and sublinear like what we would expect from Amdahls Law. However, queries in this database are split up into separate execution steps, so I also went and measured the speedup functions for each of these execution steps separately. What we find is that execution steps are either elastic, corresponding to highly parallelizable database operations, or inelastic, corresponding to sequential operations. Furthermore, if we look at the percentage of total query size devoted to elastic execution steps, and plug that into Amdahls Law as our parallelizable fraction, Amdahls Law almost perfectly predicts the average speedup function of the query. This indicates that these inelastic phases are really what's limiting the scalability of the query in this case. And if we repeat these experiments with several queries from the star schema benchmark, we see the same patterns with queries composed of elastic and inelastic phases. So to return to our original question, we're going to have to devise a model that allows us to determine the benefit that one of these jobs receives from running on multiple cores at any moment in time. In particular, we'll consider jobs composed of multiple phases, where each phase is assumed to either be elastic or inelastic. A phase here will have an associated phase size and speedup function, just like a job did in the speedup function model. In particular, we'll assume that elastic phases are perfectly parallelizable and follow this blue speedup function, while inelastic phases are completely sequential and follow this red speedup function. To model the phase structure of each job, we can think of a job as looking something like a continuous time Markov chain. There's an E state that denotes that the job is in an elastic phase, and an I state that denotes that the job is in an inelastic phase. We'll then allow a job to have arbitrary transition rates between these phases, as well as picking an arbitrary starting phase. To model the completion of a job, we'll allow one special completed phase, which is represented by an absorbing state in our Markov chain. We'll generally assume that jobs complete following an inelastic phase. This was common for the database queries we looked at, where the results of elastic computations generally have to be coalesced by some sequential work. Finally, I'm interested today in the case where the type of each job's current phase is known to the scheduler. This is certainly the case in our database example, where the phases of a query correspond to execution steps which are visible to the system. So now that we understand how a query will benefit from running on additional cores, I want to think a little bit about this second question of how we should be splitting cores between queries arriving to the system over time. And in particular, I want to think about how a scheduler should leverage its knowledge of the current phase of each running query. For example, it should be pretty clear that the phase unaware scheduling policies developed under the speedup function model can make some pretty bad decisions. For instance, consider the equi policy, which has been widely discussed in the literature. Equi divides cores equally at all times. So in this case, equi would allocate 4 cores to each of the queries currently in the system. Intuitively, under the speedup function model, equi seems like it maintains good system efficiency by preventing any one individual query from moving too far to the right on its speedup function. However, if we can see the current phase of each query in the system, it's clear that equi is over-allocating to queries 1 and 4, which receive no benefit from running on additional cores. In general, equi and other phase-unaware scheduling policies will tend to over-allocate to inelastic phases. Of course, database designers have recognized this problem, and many databases do some form of phase-aware scheduling. In particular, I'll continue to talk about the noise page database, which uses a scheduler based on the idea of morsel-driven parallelism. Noise page uses a policy that I'll refer to as phase-aware first-come, first-served. This policy processes queries in the order in which they arrive to the system, but avoids over-allocating to inelastic phases. In this example, PAFCFS would look at the earliest arriving query, query 1, see that it's in an inelastic phase, and allocate it only one core. It would then move to the next query in the queue, query 2, see that it's in an elastic phase, and allocate it the remaining 15 cores. Then, when query 1 completes, its core will be reallocated to query 2. Because it's phase-aware, PAFCFS is clearly not wasteful in the same way that Equi was. Still, the question remains, can we beat this phase-aware policy that's used in modern databases? We find that there are two key ideas in designing a good phase-aware scheduling policy. The first idea is that we should defer parallelizable work and give priority to queries which are in inelastic phases. The intuition here is that we want to avoid situations like this example, where we only have inelastic phases to work on, and therefore we aren't able to fully utilize the available cores. If we go back to our original example, the allocation I'm showing here is deferring parallelizable work by giving priority to queries 1 and 4 which are in inelastic phases. We can then take any leftover cores and allocate them to a query in an elastic phase. The second of our key ideas here is that we might want to prioritize shorter queries. That is, we might want to work on queries with smaller remaining total sizes, since this is generally known in the scheduling community to reduce mean response time. Now you'll notice that I've bolded the first of our two key ideas here, and that's because we can actually prove that under certain conditions, just deferring parallelizable work can result in an optimal phase-aware scheduling policy. Without getting into the details of the proof, we define a policy called Inelastic First, or IF, which gives strict priority to jobs which are in inelastic phases at every moment in time. We then assume that jobs evolve according to some underlying Markov chain like what we saw earlier. Specifically, we assume that phase sizes are unknown and exponentially distributed. And while the scheduler can see the current phase of each job, it doesn't know the exact sequence of phases for each job a priori. In this case, we can construct a coupling argument to show that Inelastic First is optimal with respect to mean response time. Of course, this begs the question as to what a good phase-aware scheduling policy looks like when any or all of these assumptions are violated. In particular, what happens if we're in the case where the database knows the exact sequence of phases corresponding to each query, or the database can make very accurate predictions about the sizes of each query phase? In this case, we have to actually combine our two key ideas and work on shorter jobs in addition to deferring parallelizable work. To accomplish this, we propose a policy called IF-SRPT. IF-SRPT still gives strict priority to inelastic phases in order to defer parallelizable work. However, within the group of jobs which are in inelastic phases, IF-SRPT gives priority to the phases belonging to jobs with the shortest remaining total sizes. Any remaining cores can then be allocated to the shortest query which is in an elastic phase. You might wonder whether it's even worth it to defer parallelizable work in this case. We could consider a phase-aware SRPT policy, which avoids over-allocating to inelastic phases, but otherwise prioritizes the jobs with the shortest remaining total sizes. To illustrate the importance of deferring parallelizable work, I'll show you the results of simulations that we ran based on the star schema benchmark numbers I showed earlier in the talk. Note that these queries frequently violate the assumptions made in our theoretical model that I described earlier. Unsurprisingly, the mean response time under a phase-unaware policy like Equi is off the charts. If we look at phase-aware policies, we see that even though IF is not optimal because we're violating our theoretical assumptions in this case, IF still outperforms PAFCFS by about 30%. If we consider the case where the scheduler knows the size and structure of queries, we can further improve mean response time by using IF-SRPT. Surprisingly, phase-aware SRPT does even worse than first-come, first-serve because it fails to defer parallelizable work. So to wrap up, today I discussed the Speedup function model and how it could sometimes hide the fact that jobs can be composed of elastic and inelastic phases. I presented a model for these jobs composed of phases and used it to motivate the design of better phase-aware scheduling policies. I presented two key ideas in the design of better phase-aware scheduling policies and showed that IF, which just defers parallelizable work, can be optimal in certain circumstances. In other cases, IF SRPT, which balances our two key ideas, can perform well in practice. Thank you, and I'll now take any questions.